So by the end of this lesson, I want us to be able to take information about a function, about its derivatives, and construct what the function probably looks like based on that information. So the problem's going to look a little weird. You're going to get like 6 or 7 statements worth of information about the derivative, about the second derivative, about the original function, with no actual statement of the function, and you're going to have to come up with what the graph of that original function looked like. And I'm of the opinion that one of the best pieces of information I can give you here is that every function is basically constructed of 4 different building blocks. And these are what those building blocks are. If you have a section of a function where f is concave up and decreasing. Well, remember, being concave up means you're sort of in a smiley face part of the graph. So if you're concave up but decreasing, it means you're looking at just this part of the graph, right? So that's one of the building blocks. If f is concave up and increasing, it just means you have the other part of the smiley face, right? And the last two hopefully are clear. If f is concave down, and I'm actually going to go with increasing this time. We know concave down means we're looking at the sad face part of the graph. So concave down and increasing means you've got a curve that looks like that. And the last one, f is concave down and decreasing, means you've got the downward sloping part of the sad face. So you've got this. And the statement that I'm making is that every function can be constructed using these pieces, right? And if I could even just kind of give a quick example of that. You know, if somebody said, well, I've got a function like this. Is that really made up of those pieces up there? The answer is absolutely. This part right here is an increasing concave down part. This part here is decreasing concave down. Then it turns into decreasing concave up. And then it changes into increasing concave up. And you might be looking at it saying, well, yeah, but, this one here is a really tall one, and these ones are short ones. Sure, but the idea is that these 4 function pieces can construct any function. And that even includes things with, strange asymptotes. If we take a graph that looks like, something like this. Right? This is still, this thing is increasing concave down. This is decreasing concave down. And notice it's got that curve to it, just like up above I said it was going to look like that. This is decreasing in concave up. This is increasing in concave up. And so the idea is simply we can construct functions using these pieces, and if you can get these 4 pieces memorized and where they come from, like the fact that they're concave up decreasing, concave up increasing, and so on, it's going to be easier for you to construct these functions that we're going to look at. I've got 3 examples that we're going through here. I know this video is a little on the long side, but I feel like getting to do multiple examples and seeing a number of them is really helpful. So let's get to that. Alright, so in this example, I want us to graph a function f for which all the following statements are true. Right? And at first, this looks like a whole lot of daunting information. But again, I'm going to try and give us a process for this, right? So first things first, we sort of start by drawing an axis to work with, right? And the idea is that I want to kind of underneath the graph, I want to write down what all of this stuff means, and at the end I'm going to put it all together, right? So the first thing here says that f is defined for all values of x and f of negative 4 equals 10. So what that means to me is that, at negative 4, we've got a point way up here at 10. So that was sort of my first piece of information. And in terms of it being defined, you could even draw a little line down here that sort of says for all values, f is defined. And what does that mean? That means there's not going to be holes, there's not going to be any asymptotes, no problems like that, right? So f is defined everywhere, right? Let's move on to the next thing, and maybe I'll do this do this next part and these next few in red. The next thing says that my derivative is greater than 0 between negative infinity and negative 4, and between 2 and infinity. So what does it mean if the derivative is greater than 0? Well, that means the function is increasing. So what we can sort of say is, like, again, down here underneath, between negative infinity and 4, I'm going to be increasing. And then between, if this is 1, 2, between 2 and infinity, I again am going to be increasing. Right? Then we go on and we look at this next thing. This next statement says that the derivative will be negative between negative 4 and 2. Alright, so this is convenient. Between negative 4 and 2, my function is supposed to be decreasing. Okay. Next up, and I'll start using blue for this. Next up, this next statement tells me that my derivative is 0 at negative 4 and 2. And I just noticed this is about the derivative. Derivative is 0 at negative 4 and 2. So at negative 4 and at 2, my graph is supposed to be flat. And I'm sorry that my writing has to be so small here, but there's a lot of information to fit in. The graph has to flatten out in those places, and I hope as you guys are noticing this, you're like, hey look, the graph changes from increasing to decreasing. There's a flat spot in between. That's probably going to be a maximum type thing. Here we go from decreasing to increasing, and it's flat in between. Great, that's probably going to be decreasing to increase. That's probably going to be a minimum down there. We'll sort of check that out in the next section. These next two statements are about the second derivative, so I'm going to switch to a different color for that. The first one says that the second derivative is positive. The second derivative is positive between negative 1 and infinity. Okay, so between negative 1 and infinity, my second derivative is positive, so that means I'm concave up. And the last statement here says that the second derivative is negative between negative infinity and 1. Okay, so between negative infinity and negative 1, my graph is concave down. Okay? So now the next section, the next part of this is we now have to graph this thing. Like we've taken all that information, we've written it in words, and now I need to graph this thing. And the idea is that in each of the different sections of this thing, my graph is going to look different, right? So if you look down in the section down below, here it's increasing, here it's concave down, which means in all of this region here, my graph is increasing and concave down. What does an increasing concave down function look like? What we said on the previous page, increasing concave down is supposed to look like this. Right? And you'll notice I made that a lot taller and skinnier than I did on the previous page, but that's fine, those things can all be stretched. For this next little section in here, my graph is supposed to be decreasing and concave down. Well, decreasing and concave down looks like this. That's decreasing and concave down. Okay? As I keep going, I now need to be decreasing and concave up. Well, decreasing and concave up looks like this, and that goes all the way over to there. And then in my last section here, I've got increasing and concave up. Increasing and concave up is supposed to look like this. And so that's my sketch of what this graph looks like. Now, if you did this on your own, you might have ended up having this minimum come down lower. That's fine. It doesn't really matter. I mean, in the instructions for this problem, it said that we want to find a function that meets these requirements. And so you're not looking for one right answer. We're just looking for, can we put all these pieces together and come up with a graph? Hopefully that made some sense. We're going to go into our next example now, so let's see if any of that stuck. So same deal. I want us to graph a function g for which the following statements are true. If you're feeling up to it, I'd say pause the video and sort of, try this out and see where you get. Again, I'm really going to stick to the things that I said before. We start with a graph. It says that g of x is defined for all values of x except 2. So that means that at 2, there will be no point. but everywhere else, my function is defined. Right? But because they said that g of x is not defined at 2, I should expect to see no point at all here at 2. Right? Next up, it says g of 0 equals g of 4 equals 0. Sorry about that. That statement there effectively means that you have the points 0, 0 and 4, 0. Right? 0, 0 is right here. 4, 0 is right here. So for as much as we're not going to have a point here, we most definitely have points here and here. Right? My next two statements are about the derivative, so just to make things more clear here, I'm going to use a different color. I'm going to use red here. The first one says that the derivative is negative between negative infinity and 2. So between negative infinity and 2, the place where there was no point, my function g is decreasing. Right? Then the next one, it says that the derivative is greater than 0 between 2 and infinity. So between here and infinity, g is increasing. Okay? For the next section, the next part is about the second derivative now. This says that the second derivative is greater than 0 for all x other than 2. So that sort of means everywhere except at 2, g is concave up, right? Because that's what it means for the second derivative to be positive. So now that I have this information, I'm really seeing that this graph effectively only has, it sort of only has two sections to work with, right? There's a section here where the graph is decreasing and concave up, and then a section here where it's increasing and concave up. And I know that there has to somehow be no point here at 0. Like, I can't have a point there at all. So there either has to be a hole or an asymptote, and there are going to be a couple of different options here. I'm going to go with one of the possible options. So my function is decreasing and then concave up. Decreasing, concave up. So I need a happy face graph that's decreasing. So happy face graph, so happy face could be like this, but that's increasing. So happy face decreasing has got to be like this. So I'm going to go ahead and draw a function that does that, passing through the point that I have, and I'm going to go ahead and act like there's an asymptote here where there isn't a point. There doesn't have to be an asymptote, but I'm going to go with that. In the next area, it's increasing and concave up. So again, I need, and I just realized that thing that I just drew is totally concave down. That's not what I wanted at all. So that's fine. I'll demonstrate what you're supposed to do now. You are supposed to erase that thing, except I can't erase it because the eraser tool in this breaks sometimes. Well, that's a bummer. I can't erase, so I'll go back and draw the rest of this thing in a bright green color to indicate that that's the right answer. Hopefully you guys caught that as I said it. I need it to be decreasing, but I still need it to be concave up. Right? Decreasing and concave up looks like decreasing and concave up. Decreasing and concave up. It's going to look like this. That's what decreasing and concave up looks like. So it sort of feels like it's not going to work for me to go towards an asymptote here. I'm probably going to have this thing run into this and maybe have a hole here. Let's go on and look at the next section. I'm really sorry for that confusion. Here, I want my function to be increasing and concave up. So increasing and concave up means that I want it to be a happy face that's increasing. So happy face increasing should just mean I've got something like this going on. Right, so again, I'm sorry for that black line that I've got in there that's messed up. This seems like it meets all the requirements. And it's kind of appropriate that I made a mistake on this thing. That's not uncommon. You're going to start to draw these things and realize, wait a minute, that was wrong. So please do these in pencil or use an iPad app that allows you to erase things consistently. I do have one more example for us. I know this video is on the long side. If you know you've already got the hang of it, then try out some of the ones in the homework. If you feel like you're not sure you got it, go on and look at the next one, because this is definitely something that takes practice. It's a challenging thing. And if you really need to, pause the video for like 15 minutes. Go do something else and come back to it. So let's look at this last example.